Hi, everybody. Today we're going to be talking about torques and static equilibrium, and we have a fun little problem. We're going to solve it step by step and break it down for you. So our question is given, Jack wants to cross a stream on his hike and places a plank of wood, mass of which is 170 kilograms, against a vertical frictionless cliff over here. The plank is at theta equals 32 degrees, and its center of gravity is 1/3 of the way down its 5-meter length. And the coefficient of static friction here is mu k equals 0.95. Now, if Jack is 100 kilograms, what is the maximum mass he can have in his hiking pack? All right, so let's do this problem. So here I've drawn out a diagram with all the forces. Now, this isn't a real free body diagram, but it'll give you guys a good idea of what the forces are acting on this log. Now we've set our pivot point to down here, which will eliminate our normal force here and also the force of static friction. But I'm not going to delete that just yet because that'll be important later. There are forces acting on this log, and we know that the sum of all the torques equals 0. Now we know this because if the sum of the torques weren't 0, the log would fall into the water, and it wouldn't be a very good day for Jack. There are 3 torques in total, right? We have the torque going clockwise from Jack and his force of gravity on the log. We have another torque clockwise, which is the mass of the log here, and then the force of gravity. And then we have a torque going counterclockwise, which is given to us by the normal force of the log against the wall. Now that force is equal to our force of static friction. We'll get to that later, so don't worry about that just yet. Right now, we're just going to worry about the torques, right? So we know that the sum of the torques is 0, which means the torques going counterclockwise and the torques going clockwise are equal. Now here we have a torque going clockwise, and one of those torques is, let's say, the torque from the log, right? Now, we add that to another torque going clockwise, our other torque, which is our torque from Jack and gravity. From those torques, we're going to subtract the torque going counterclockwise, which in this case is the torque of the normal force against the wall. All right, now we're going to combine these two equations so we can say that the sum of the torques, the sum of the torques equals 0. We're going to add these torques, but we're going to write out the equations for them. Now we can write out the equation for torque. And in this scenario, we're going to use the equation torque equals the force times the distance from where that force is happening, in this case, the pivot point. In this case, we're going to go r for radius. And then we're going to multiply by sine of theta. Now, this doesn't always have to be sine of theta. It can also be cosine of theta. And in this scenario, we're going to be using cosine of theta. And I'm going to break that down for you guys. But first, we're just going to know that torque is force times the distance that the force is from the pivot point times the angle that is acting perpendicularly, right? Because we want to calculate here, force of gravity of Jack is going this way, but the force that Jack is acting upon on this pivot point that we care about is the force going this way. And that force of gravity can be turned into a force going this way and a force going this way, right? Because we have two components of our force. And so all we have to do is we use cosine or sine to break it into its constituent forces. So here we're going to write out our formula, right? We have sum of torques equals 0 equals mass of the log times gravity times L over 3 cosine theta. So we have mass of the log times gravity, which is the force of gravity, right? And then we have L over 3, right? That's the distance that we have from the pivot point, because remember, the center of gravity is 1/3 of the way down. Now we have L over 3, and then I used cosine theta. Now I used cosine theta because we have force of gravity, here's the log, and we want to know the force going this way, right? We want this force here, and that's the base, right? And cosine, or this is the adjacent side, I guess. Cosine is adjacent over hypotenuse. Remember your SOHCAHTOA, right? So pretty simple. That's our cosine. Okay, so that's our force of the log and gravity. Now, we're going to add to that, we're going to add the force that Jack has clockwise. Now, this is going to be pretty similar, right? Because we're still using this formula over here. We're going to be using mass of Jack times gravity times the length that Jack is along the log. Remember, if Jack is over here, he's going to be exerting a lot less force on the pivot point than if Jack is over here. times cosine theta for the same reason as before. Now, all we're going to do is we're going to subtract the forces going counterclockwise now, right? The force normal against the wall. Now, in this case, we know that the force normal against the wall is equal to the force of static friction. And we know this because the log isn't moving, accelerating in one direction or the other, right? And these are the only two forces. So this is a quick, nifty little trick we can use. We can use the formula for the force of friction over here, right? As our force of to get our force normal 1, I guess, over here, because there's also our other force normal that we deleted earlier because we set our pivot point to here. So in this case, we're just going to say minus force of normal 1 times L times sine of theta. Okay? Now we used sine of theta because when you look at this, you're breaking it into its constituent forces. This is the force that we want, the force going that way. And for angles here, we know that theta here, or sorry, theta over here is equal to theta over here, and sine is opposite, which is this side, over hypotenuse. So we have a formula. All we have to do is isolate mass of Jack. Okay, so let's get to solving. The first thing we're going to do is we're going to take this force of normal 1 that we have over here, and we're going to replace it with something a little more useful, because right now we haven't decided what that is. Now we know that the sum of forces in the x direction equals the force of static friction minus the force normal equals 0. Now, by this saying, this is just what we said earlier, the force isn't going one way or the other. So we know that the force of static friction equals force normal friction 1, and the force of static friction is given to us by force of friction equation, which is mu s times force of normal, which is the vertical direction, which will equal mass times gravity. Now remember, this mass isn't any mass, it's the mass of Jack plus the mass of the log, right? So now all we have to do is we have to plug this equation into this equation. All we have to do is solve. Now we can cross out gravity and L here because they're in all of our equations. And that leaves us with mass of log over 3 times cosine of theta plus mass of Jack times cosine theta minus coefficient of friction times mass of Jack plus mass of log times sine theta equals 0. Now, all we have to do is isolate for our mass of Jack. We end up with the mass of Jack equals the mass of the log times mu s sine theta minus 1/3 cosine theta over cosine theta minus mu s sine theta. Okay? Now we can simplify this, and now we have our equation. All we've done is we've done some rearranging of our formulas, and we've gotten to here. All right, so now that we have our equation, we can plug in our numbers. I've moved over here, so I'm going to take this equation. I'm just going to shift it over to here. Okay. Now, all we have to do is plug in our numbers. Now we know that L equals 5. Our mass of the log is 170, and so on and so forth. So we're going to go 170 times 9, 5, tan 32 minus 1/3. And we're dividing that by 1 minus 0.95 tan of 32. Now, this is going to give us the total mass that we can have on our log, or the mass of Jack, I believe. Now, we know that the mass of Jack is 100 kilograms. So I guess a better label for this would be the mass of Jack plus his pack. So we also have to remember that we're taking 100 and we're subtracting by the total mass of Jack to get our mass of our pack. Okay, so when we plug in all these numbers, we get the answer of 8.889. And we can just say that's 9 kilograms. Okay, and there you have it. We've solved the question. The maximum mass that Jack can have in his hiking pack, if he's 100 kilograms, is approximately 9 kilograms. Thanks for watching. My next video is going to be about chemistry, so make sure to stay tuned.